Academic Physics, welcome back to the Simpkins Physics Corner with your host, Mr. Simpkins. It's week 9 of Academic Physics, and we're launching today. Today, I'm going to give you an overview of everything we've covered so far for problem solving with acceleration. So the first thing we realize is we get a lot of these word problems, and we need to know that words mean things. It's amazing how in physics class, and even in 2020, yes, words mean things. And so let's take a look at our first couple of things we need to know. Look at units first. Over here in the first box, what I want you guys to do right now is to go ahead over to your Canvas page and to download this before we start. Download this right now. Week 9 launch, problem solving recap, acceleration problem solving cheat sheet. Go do that right now because that is where you will find this. So hit pause if you need to, go get that. And we're back. So let's take a look. What are the units that you should use or look for when you're reading a problem? Well, if you see the units of seconds, we're talking about time. So that would be t equals something. If you're talking about distance, remember we like d from the first unit. Speed is distance over time. But remember that distance or displacement, how far you are from where you started, also has to do with meters. So if you see meters, we're going to be looking at xf or xi, the final and initial position. Acceleration, that's the rate of change of velocity. So if velocity is meters per second, it's going to be the rate of change going to be meters per second squared for acceleration. So if you see a horse gallops at an acceleration of 2 meters per second squared, that's your a variable. And then finally for velocity, you're going to look for meters per second. That's how fast you're going and in what direction. Then we look at, okay, what about when we're looking at variables? All right, let's say we do have some information. Well, time is going to be t equals some number of seconds. Distance, xf, the final position there. Acceleration is a, vf is final velocity, and vi is initial velocity. So if you don't know what these variables mean yet, you have no prayer at using the equation sheet properly when you solve physics problems. However, if you put the time and effort in on the front end a little bit, maybe make some flashcards, maybe just do a few practice ones, maybe go back to last week and watch some of our lesson videos, you'll get up and caught up real quick. Now, words mean things. So when we were reading a word problem, let's look at some phrases that tip us off to things. Like, let's consider this phrase, comes to a stop. Well, what does that mean? That means it's at the end of the problem, because I'm coming there, right? That's where I'm ending up. And a stop describes how fast I'm going. And if I'm stopped, how fast am I going? 0. So if you see a phrase like comes to a stop or comes to rest, that's telling you VF equals 0 meters per second. How about starts from rest? Well, that's telling you VI is 0 meters per second. What if something says travel at a constant speed? Now, you probably won't see many of those because we're in our acceleration unit, but if you did, it would tell us that the acceleration is 0 because we have no acceleration if you're at a constant speed. Moving backwards would tell you that your velocity is negative. Moving forwards would tell you that your velocity is positive. And if a question is asking for you to solve something like how long does it take, English language is weird, right? How long is this? What, you mean in meters, or how long did it take in seconds? That can be confusing. But if it says how long does it take for a rocket to shoot 500 meters, you would solve for time. How far does it travel? You would solve for xf. A lot of people are like, oh, I got to get distance, got to go. And then they get into chapter 2 equations, and those don't work for acceleration, and they get all kind of problems. And then how fast is it going? That would be solved for vf, like how fast are you going a little bit later. So there's a quick little overview. Take a moment, pause it if you need to, and make sure that whole sheet is filled in for the acceleration problem solving cheat sheet. And keep this one with you as you're reading our word problem. And we proceed. Let's go to the next little piece here. I assigned you guys the concept builders. If you're asking, Mr. Simpkins, what's a concept builder? Then you're behind the 8 ball, because last week in the module, I had asked you guys to go ahead and do this. Let me show you where it is real quick. If I go to modules, which you always can do, and this was also posted on your calendar, so you didn't miss it. But if you go to our modules here, this was in week 8, and it says right here, week 8, asynchronous 2. That would be the second day you weren't in school. It wasn't a launch day. Acceleration concept builder. There it is right here. So I have some directions for how to start your concept builder account, and then there are little secret codes here for you guys. But I was getting some questions, so I did post a little short video with some helpful hints there for the concept builders, but I just wanted to go over that one more time with you as we were all here together. Acceleration is defined as the change in velocity over time. So if I write on here, it would be acceleration equals delta v over t. Now, remember, velocity is a vector. Velocity is a vector, but let's start with v. And if it's a vector, that means it has both magnitude and direction. Oh, yeah, it does. It's just true. And so the acceleration equation is vf minus vi over t. Looks a little something like that. So let's look at these two side by side. These were 2 of our concept builder questions. Look at this first one. This thing's moving left. So right away, we have to remember, if you're moving left, that means your velocity is negative, because left is one of those negative directions. It says, what's the magnitude and direction of acceleration? Okay, so let's take a look here. Since the car is moving to the left, this would actually be our VI. So what we're seeing here is our VI is actually negative 20, Do you catch why? It's because that's how fast we're going at the beginning of the problem, and we're going to the left, so that's why it's negative. And then VF is going to be 4 meters per second, but we're going to the left, so I got to make it negative 4. And then our change in time is going to be 2 seconds, because that's how long it took to go from the first picture to the second picture. So if we take that information, we plug it into our acceleration equation, it looks a little something like this. VF, which was negative 4, minus, now this is where it gets crazy, minus VI, that's minus negative 20 over 2. And so if you can algebra good, you may have heard this term keep, change, flip, right? If you subtract a negative, it's like adding a positive, right? So negative 4 plus 20 would be 16 over 2, or our answer here would be 8 meters per second squared. So the magnitude is just the number. You notice it says no sign. It doesn't want positive or negative there, so if you get a negative answer for a different problem, don't put it there. But let's talk about what this means. If you're moving to the left, all right, it's this way on your screen. If you're moving to the left and you're slowing down, which way is your velocity changing? Well, if you have leftward velocity and you are losing it, that's because you're accelerating to the right. Your velocity is changing to the right, and to the right is positive, and so that's why this is actually the 8 meters per second squared to the right. If we set up our positives and negatives correctly at the outset, they kind of handle themselves. So that's a little example for you guys. What we would say here is that your acceleration is to the right because your velocity to the left is changing. That's slowing down in this case. Let's try again. The velocity timetable represents the motion of a rightward moving motorcycle. So right away we know we have positive velocities. And it says what's the magnitude and direction of the acceleration. Now we have a whole table of values, so you really could pick any pair of data points. If you guys will recall, if you have a velocity time graph, you could take the slope of that to find the acceleration. Cool little trick there. But let's just go ahead and pick 2 points. Let's do the first one and the last one. Why not? What we notice here is our initial velocity is 24 and our final velocity is 8. So right away you're like, oh, we're slowing down and we're moving to the right. I hope you're thinking acceleration is to the left or negative. Let's see if that pans out here. If I take this equation, VF minus VI over T, let's see, we have 8 minus 24 over, we went from 0 to 2 seconds, so that's 2 seconds total, and 24 minus 8, or 8 minus 24, I should say, would get us a negative number. And it's still early, so I don't want to depend on my mental math skills quite yet. And that would be negative 8. Now, here's where people trip up in the what do you call it, concept builder. They try to take their answer, and they try to put the whole answer in there, but what does it say? It says no sign. You are not allowed to put a sign there. So the magnitude is 8, and the direction, if you tap on this, it'll give you the choices of right or left. Well, our answer was negative, so which direction should I pick? I should pick left. So that's 2 examples for those concepts builders to help you guys out. They're both getting at the big equation right here. Acceleration is defined as change in velocity over time. So that's the easy version. But last week we were looking at these equations, which get pretty beast pretty fast. So I'm going to show you one today, and then your job after that is to do one of them and turn it in on Canvas for me. So if we go back to our Canvas here real quick, and I go to my, well, you can go to the modules here. It's going to be on the calendar for you guys as well, as it always is. But if you look at Week 9 Launch Problem Solving Recap, right here is the problem. I want you guys to download this. I want you can put it in a Word document or a Google Doc or print it out or write it out. That's fine. Any one of those, whatever works for you. I want you to show me the 5 steps of the problem solving. That means underline the knowns, write the list of knowns of the variables, identify what you're solving for. You can circle it in the problem or something. Pick the equation, plug the numbers into the equation, and then go ahead and solve for that final answer with the units and variables. So that's your job for today, is to turn that into me, to show me that you know what you're doing after today's lesson. But let's real quick do one more example, so we have lots of examples to choose from. There's plenty from last week as well, if you want to check some of those out. So an NPC rushes toward a bronze door. If it accelerates at a rate of 0.5 meters per second squared and starts charging with a velocity of 1.5 meters per second, how far do they travel in 9 seconds? So let's go ahead and capture all of our numbers. We have 0.5 meters per second squared. We have 1.5 meters per second, and we have 9 seconds. Do you guys now see why it was so important with what we started today? If you don't know what meters per second squared represents, this is going to be much more difficult for you. But we do know what it represents. In fact, context clues here, if it accelerates at a rate of, right, so it tells you right there, so that's our A. It says starts charging with a velocity. That's going to be V initial, because that's the beginning of the problem. And then the time here is 9 seconds, and it says how far do they travel. Now, if you're duped into putting d, you notice that there's no d, there's no distance in any of these equations. You're going to get lost really fast. So that's what we're looking for is xf. Now, remember the cool little rule here. If the problem doesn't specifically tell us where we start the problem, we can make xi only equal to 0 meters. You can't make everything equal to 0, but you can say, hey, let's start at the origin. Let's start at xi equals 0. So you can do that. Now, remember the mantra from last week, ladies and gentlemen. Sometimes what you don't know tells you more than what you do know. And what we don't know in our list of knowns is VF. So I can't use this equation, I can't use this equation, and I can't use this equation, so I must have to use this equation. All right, follow that again. Our list of knowns, of course we don't have XF because that's what we're looking for, but we don't have VF, so we can't use any equation with that. That's the key, ladies and gentlemen, to unlocking the answer to the age-old question of physics students. Mr. Simpkins, how do I know which equation to use? Well, simply find the equation that doesn't have the thing that you don't know and use that. So let's see if we can go ahead and execute this one here then. We got 0.5 meters per second squared. The time is 9 seconds. And a special note, only the 9 gets squared. A lot of people want to square that whole thing. Notice it's just t squared. It's not at squared, it's t squared. So only square the time there. Then we're going to add on our initial velocity, 1.5 meters per second. Again, multiplying that by 9 seconds. And then plus 0, because if the xi is not given, we can set it to what we want. We can set it to 0. Why don't you go ahead and pause the video, grab your calculator. You can use the VTI-83 on your computer or the calculator you have at home. Go ahead and pause the video right now and solve for the final position. And if you do it correctly, you should be getting 33.75 meters. That's how far they traveled in 9 seconds. All right, so here's another example. And if you still need more examples, go back to week 8 last week. Look at all those examples that I did for you guys and follow along there. All right, so there's the basics. There's acceleration equations on your equation sheet. And then there's the next level, which is what we did last week. And this week, we're going to wrap up all this stuff and give a quiz on Thursday and Friday, depending on your live day, where I'm going to assess. You're going to have to do one of each of these. All right, so you're going to have to use one of each of these equations to solve a problem. You really need to know what you're doing, or you're going to be completely lost. So in moving towards that goal of knowing what you're doing, what I want you guys to do for today, again, is you're going to go to your Canvas. You're going to go ahead and complete all this stuff that you're working on as we saw here today. And I want you guys to snip this or whatever, do this problem, and then submit it to the assignment. It'll say like zombie warm-up or something right underneath of here. Just go ahead and submit that, and that will be your duty for today. However, if after today's lesson you're still like, oh my goodness, Mr. Simpkins, I'm super confused about stuff, this would be a great time today to use some of your time that you have to go back and look at some of those lessons from last week that we had examples for. All right, so if I can figure out how to end this recording, then I will do so here momentarily. There it is. And so until next time, ladies and gentlemen, this is Mr. Simpkins in the Simpkins Physics Corner.